Good afternoon, Mr. Muhammad. Today, inshallah, we will continue talking about eigenvalues, eigenvectors, part 2, and we will be talking about diagonalization of matrices. This lecture is really very important. It contains valuable informations about how to evaluate the eigenvalue, eigenvector, and how to do diagonalization for matrices. The algebraic multiplicity, the geometric multiplicity will be defined in this lecture, inshallah. Of course, all of our course resources and the recorded videos, you will find them on YouTube, and also all the lectures, you will find them in Moodle. For the eigenvalues and the eigenvectors, as I told you, we will start this part today. In the previous session, I've given you how to evaluate the eigenvalues and the eigenvectors from the characteristic equation. If you remember, getting the determinant of a minus lambda I, which means you will subtract lambda from the elements of the principal diagonal. Then you will try to expand your determinant, put it equal to 0, and you will solve. Now I will answer some of the main questions. What's the reason for the use of eigenvalues and the eigenvectors? Well, actually, there is a lot of answers, but for us and with our applications, we will go through dynamic systems. Hopefully next time, inshallah, I will try to do this on next Wednesday. Which is easier to deal with? Having a matrix on this form, which is a diagonal matrix to the power of 10. If you try to multiply diagonal matrices in itself, you will end up multiplying the elements of the principal diagonal. So mainly it's going to be t to the power of 2 to the power of 10, 3 to the power of 10, negative 1 to the power of 10, and that's it. Other than dealing, or not even comparable, with dealing with a matrix 3 by 3 multiplying itself 10 times. So it's going to be horrible. So dealing with matrices on the diagonalization or in diagonal form, it's much simpler and more direct than dealing with matrices on the main form. There is a way to simplify the computations on the second matrix. So I can find a way to replace this matrix by an equivalent one, but it's a diagonal matrix. We will see this today. So two matrices A and B are similar if there is a matrix B such that B is equal to B minus 1 A times B, and in this case the B matrix is going to be diagonal matrix. So if I succeeded in finding the P matrix, which is surprisingly, it is the matrix that I can form or find from the eigenvectors that we saw in the previous lecture. So if I can do that, I will be able to change A into a diagonal matrix with the eigenvalues as elements on the principal diagonal. If A is similar to a diagonal matrix, then we can take advantage of its properties. That's the bottom line. That's why we are going through these difficulties in order to find the eigenvalues and eigenvectors. Now once more, let's start getting back to the main slides. Of course, what I've tried to explain previously, it's written here. A diagonizable matrix, if a matrix is said to be diagonizable, if there is an invertible matrix B, so B you will have to get its inverse, such that the A matrix is equal to B times D times B minus 1. By the idea, if you multiply this relation by B from the right and the B minus 1 from the left, you will end up having a diagonal matrix. You can get a diagonal matrix which is equal to B minus 1 A dot B, which means I can change any matrix A, if it is diagonizable, as we will see, by multiplying A in the inverse of the matrix B from the left and in the matrix B from the right. These two equations are equivalent to each other. And we will see it is handleable and we can do it easily. So once more, as I told you, this is the first slide. Similar to what we have been through, that B is equal to A minus 1 AB. That's the formula that we wrote already. If you want to multiply, if you want to get A squared all I have to do is to multiply ADB minus 1 in A, which is BDB minus 1. If you remark, having this multiplication, the P and the P minus 1 will eat each other. You will have D times D, which is D squared, and you will have B minus 1 times B. If I want to get A to the power of 3, it's exactly the same. I will multiply here also by P, D, P minus 1. And in a similar manner, Mr. Muhammad, B minus 1 and B, they will eat each other, and you will have B, D cubed times B minus 1, which is really can be generalized, and it will make your life easier. Reaching A to the power of K is equal to B, D to the power of K times P minus 1. The question is how to get the P matrix and how to get the inverse of the P matrix, which this is why we will see the following steps. So simply and once more, for a matrix on this form, which is 4, 1, 2, 3, double 2, negative 7, 1, negative 3, I can find a P matrix. In this form, this is the P matrix minus 1, and that's the P matrix. If I multiply B minus 1 times A, this matrix, times the B matrix, that we will see how we will bring it, you can have a diagonal matrix of this form. If you remark for this diagonal matrix, you will find the elements on the principal diagonal are 1, negative 1, and 3. And since we already knew about the eigenvalues, we already did something like this in a 2 by 2 matrices. Once we get the eigenvalues and we multiply the matrix by the ortho normalized model matrix from the two sides, and we ended up having a diagonal matrix. So bottom line, if I could get the eigenvalues for this matrix, which is going to be 1, negative 1, and 3, and we get the eigenvectors relative to each eigenvalue, I can find the matrix B, and from which I can get this relation. The problem is now how were those matrices B and D found? Of course, through the eigenvalues and eigenvectors that I told you about. This slide for the introduction, how to use the equation, which is A times V minus lambda times V. If you take V as a common, you will end up having the characteristic equation that we used in the previous session, which is A minus lambda I times V, which is equal to 0. And this is how we can get the eigenvectors values from here, which are the lambda values, and also corresponding to each value of lambda, I can get the values of the eigenvectors assigned to each eigenvalue. Okay? So this is mainly the equation that we saw in the previous session. So let's start, okay, on a problem in order to validate all of this. Of course, this is also explaining to you the eigenvalues, the details that I told you about, and the eigenspace and so on. What we mean about geometric multiplicity, it's a very important definition. The geometric multiplicity is of lambda is the dimension of its eigenspace. Once you get the eigenvalue, you have the form of the span of the eigenspace. The number of vectors in this span, this is what we call it geometric multiplicity. For the algebraic multiplicity, it is the number or the repetition of the values of the eigenvalues when we solve the characteristic equation. Of course, A minus lambda I is called characteristic polynomial. If this polynomial is equal to 0, it will be called characteristic equation. And from this equation, we can get the values of lambda as we saw previously. And the algebraic multiplicity of lambda is its multiplicity at the root of the characteristic equation. How lambda is repeated in the characteristic equation. Let's see this example. I need to find, and I want to go with you step by step, how to find or how to solve in order to get the eigenvalues and get the eigenvectors. It's really very simple. If I want to get the eigenvalues, all I have to do, Mr. Muhammad, is to start with A minus lambda I, which equal to 0. That's the characteristic equation. If you try to substitute with this matrix in this form, you will end up having the determinant of the matrix that I told you about, which is gonna be 4 minus lambda, then 3 negative over 7, then 1, 2, then 2 minus lambda, then 2, 1, negative 3 minus lambda, and it's all equal to 0. If I want to evaluate the value of this determinant, it's really very simple. But you have to be well organized while you are trying to evaluate the value of this determinant. So I will start with you. 4 minus lambda times 2 minus lambda times negative 3 minus lambda. I believe you will have negative of 4 minus lambda, am I right? Times 2 minus lambda, I'm using Sarah's rule, if you remember. Times 3 plus lambda, because I've taken the negative from this element outside. I've multiplied the elements of the principal diagonal. Then 1 times 2 times negative 7. Am I right? So it's going to be a negative of a 14. Then I will do 1 times 3 times 2, which is going to come up to positive over 6. Then I will go to the secondary direction. And that's negative of negative 7 times 2, which is 14 times 2 minus lambda. So I will have plus 14, okay, times 2 minus lambda. Once more, negative 7 times 2 is negative 14. Times the negative of the secondary diagonal is going to be positive. Times 2 minus lambda, as you can see. Then I will have 1 times 2, 1 times 2 times 4 minus lambda. So I will have plus 2 in 4 minus over lambda. Then I will have 3 times 1 times this value, which is going to be negative of a 3 of 3 plus lambda. And all of this is equal to 0. Now I will need to solve this equation. But the problem is this equation is a cubic equation. So I have to have a fast way in order to solve this cubic equation. So all I need is just to be well organized in order to evaluate the value of this equation. So I will start with these two brackets, multiplying them together. So it's gonna be lambda squared, okay, times 2 times negative 2 lambda minus 4 lambda, so it's gonna be negative 6 over lambda, plus an 8, and it is multiplied by 3 by plus lambda. I will try to expand for the time being. Lambda squared times lambda is gonna be negative of a lambda cube. Then I will multiply lambda squared times 3, which is gonna be plus 3 of a lambda squared. So I will multiply lambda squared once in lambda and once in 3. Now I will go for negative 6 over lambda. Multiplying it by lambda will develop negative 6 of lambda squared. Am I right?
No.
So it's a negative 6 times lambda. Then you have a negative sign outside, which is going to be a positive. Also, once more, lambda squared times 3, it's a 3 lambda squared times the negative outside. So it's going to be a negative of a 3 lambda squared. Now we are right.
Oh.
Then I will multiply negative 6 over lambda times the negative, which is positive 6 times 3. So I will have plus 18 over lambda. Now I will go negative 8 times 3, which is going to be minus over 24. Then minus lambda, okay, times 8, so it's going to be a negative of an 8 times lambda. Then I will try to expand those guys and writing them beneath each row. So I will have 14 times lambda, so it's a minus 14 times lambda. 14 times 2, which is going to be positive of a 28. Then 2 times 4, which is going to be a positive of a 8. 2 times negative, so it's a negative 2 lambda. Negative 3 times 3, which is going to be negative 9. Negative 3 times lambda is going to be negative 3 over lambda. Don't forget that negative 14 plus 6 is going to give negative 8, I believe. So it's going to come up to negative 8. Now I will try to evaluate the values of this characteristic equation, which is going to be negative lambda cube. Then I will have negative 3 plus 6, So it's gonna be positive, am I right? 6 of lambda squared, okay? And then I will have, you have negative 8 plus 18, which is negative 10, negative 10, and you have negative 14, negative 2 minus 3. I think there is a problem with the signs in this part. 3 times, okay, as I told you once more, we will have to review it. 3 times 8, which is gonna be a 24, 8 times lambda, which is gonna be positive 8 over lambda, times a negative 8 over lambda. This 18, it came from negative 6 over lambda times 3, which is negative 18 times negative, is gonna be positive 18. Anyhow, I will try to sum all of these values of lambda in order to have my equation. So it's a negative over lambda cubed, 3 lambda squared. This is gonna be negative 3, negative 2. It's gonna be negative of 5, negative 14. It's a negative 19 plus 18. It's gonna be negative 9. Negative positive 9, I'm sorry. Are we right? Negative 1, I'm sorry. صح؟ يبقى minus 9 over lambda. Then I will gather these numbers. Negative 8 with 8, positive 8. I will have negative 9 plus 28 plus negative 24. Then I will have the number here is equal to 0. Now I will try to solve this equation, which is negative lambda squared plus 3 lambda squared minus 9 lambda plus the number in here. So getting all of these values, which is going to be negative 24 plus 28 is going to be 4. 4 plus 8, okay, it's going to be a 12. 12 minus 9 is going to be negative 3. Negative 3 plus negative 8 is going to come up to negative 11. I believe I made a mistake in expanding these numbers. So you will have to recheck them. I will try to solve this cubic equation. In order to be able to solve this cubic equation, if I multiply in negative, it's going to be lambda cubed minus 3 lambda squared plus 9 over lambda. Then plus 11, it's going to equal to 0. Then I can try to solve this problem. As I told you, probably 100% I made a mistake in expanding these numbers, because I remember that the equation will have roots like 1, negative 1, and 3. So probably I made a mistake in expanding these numbers, but I don't want to lose time in trying to re-evaluate it. But this is how it's gonna be done. Okay. Just only in certain cases if there is no other way, like this problem. Okay? Okay. If you try to expand it, I will take a peek for the values of lambda. So it's gonna be, this is the equation, exactly as we did. So we will need to solve this homogeneous system in order to get the values of our lambda. We can study which lambda, the determinant a minus lambda I equal to 0. So I will start with writing. As I told you, the equation, the analysis of this equation, it's gonna come up to, okay, as I told you, lambda minus 1 times lambda plus 1 times lambda plus lambda minus 3, and it's gonna equal to 0. Those are the correct 3 values of lambda. So once more, do exactly the same as I told you. It's gonna be 4 minus lambda, 3, 1, negative 7 and 2, 2 minus lambda, negative 3 minus lambda. This is the 1 and 2 expanded. Try to simplify it. I've already did and get this equation. Are you with me, Muhammad? So I want you to recheck the numbers once more. Now I've ended up, I have the values, which is lambda 1, I can consider lambda 1, okay, is equal to positive 1. And lambda 2, I would say lambda 2 is equal to negative 1. And the lambda 3, of course, is equal to 3. So lambda 3 is equal to positive 3. Those are the 3 values of lambda if we evaluate it. Now I will need to evaluate corresponding to each value of these values the corresponding eigenvector of each one of them. So once more, I will start getting the homogeneous system. The homogeneous system will be this determinant or this equation, and I will replace lambda by the value. So it's gonna be 4 minus 1, which is gonna be 3. Then I will have 3. Then negative 7. For the second row, it's going to be a 1. Then 2 minus 1 is going to be positive 1. Then positive 1. For the third row, it's going to be 2. 2. Negative 3 minus 1 is going to be negative over 4. And I will try to solve this homogeneous system of equations. So, as I told you, the second step, I will try to solve this homogeneous system, which is A minus lambda I, and it's equal to 0 homogeneous system. So, I think I can replace the second row to be on the first row. So the first row will be 1, 1, 1, and 0. Then I will multiply negative 3 and add. Negative 3 plus 3 is going to be 0. Negative 3 plus 3 is going to be 0. Negative 3 times 1, negative 3, and the negative 7 is going to be negative 10, and it's equal to 0. Then I will try to get the elements of the last row. So it's going to be, as I told you, negative 3 plus 3 is 0, negative 3 plus 3 is 0, negative 3 plus negative 7 is negative 10, negative 2 plus 2 is going to be 0, negative 2 plus 2 is going to be 0, negative 2 times 1, which is negative 2, plus negative 4 is going to come up to negative over 6, and now it is equal to 0. This is the form that I have. The second step, I will try to divide the second row on negative 10, and once we divide on negative 10, I will have 0, 0, 1, and 0. If you multiply 6 and add on the last row, it will all disappear. Of course, this system must give infinite number of solutions.
Come on.
Okay? So, I have, this is the second row. I will multiply negative 1 and add on the first row. So, it will come up to this situation. Now, I will need to expand in order to get the eigenvector. I would do, this is the first vector, first component. First vector, second component. First vector, third component. And it's all equal to 0. Try to expand it into equations, which means u1 sub 1 is equal to negative u1 sub 2. That's the first component is equal to negative the second component. While u13 is equal to 0. If you remark, the first vector, or u1, it consists of the first vector, first component, first vector, second component, first vector, third component. Just to try to do the substitution. So you will have negative u1 sub 2, u1 sub 2, and u13 is equal to 0. If you take u12 as a common, you will have the following form, which is the span of the eigenvector, the first eigenvector. So for u1, the first eigenvector, which is corresponding to lambda 1, which is positive 1, you will have the span of this eigenspace, which is negative 1, 1, and 0. Are you with me? Mm-hmm. So that's the vector representing the span of the first eigenvector. Before we continue, we already have lambda 1 is equal to 1, lambda 2 is equal to negative 1, and we have also lambda 3, which is equal to positive 3, I believe, or negative 3? Positive 3. Okay? So now I have the values with me. Okay. Is there any repeated values in the values of lambda? No. So the algebraic multiplicity, it is the number of repetition. So the algebraic multiplicity for each one of them is 1. Okay, that's the dimension or the algebraic multiplicity. The geometric multiplicity is the number of vectors in the span, which is 1. As long as your algebraic multiplicity is equal to your geometric multiplicity, you will be able to diagonalize your matrix. I will do exactly the same, but in this time, I will do the same steps, but instead of having lambdas equal to negative 1, positive 1, I will use lambdas equal to negative 1. So once more, 4 minus negative 1 is going to come up to 5, then 3, then negative 7, then I will have a 0. Then for the second row, it's going to be a 1. Then 2 plus 1, so it's going to be 3. Then 1, and it's equal to 0. For the last row, it's going to be 2, 2. Negative 3 minus of a negative 1 so it's gonna come up to negative 2. I believe it's equal to 0. Once more, it's a negative 3 plus 1, so it's a negative 2. Once more, I will be moving to reach the nearest 4 to my solution, the previous one. So I can either replace the 2 rows, or maybe I can multiply this row by negative 4 and add it on the first row. Just a change. If I did so, I will have the following. Negative 4 plus 5 is going to be 1. Negative 4 times 3 is going to be negative 12. Negative 12 plus 3, it's going to be negative over 9. Negative 4 and the negative 7 is going to be negative 11 and 0. And then once more, I will multiply this row by a negative and add it on the second row. Negative 1 plus 1 is going to be 0. 9 plus 3 is going to be 12. 11 plus 1 is going to be 12, and that's going to be 0. I will do exactly the same with the last row. Multiplying by negative 2 and adding. Negative 2 plus 2 is going to be 0. Negative 2 times negative 9 is going to be 18. 18 plus 2 is going to come up to 20. In a similar manner, negative 2 times negative 11 is going to be positive 22. Positive 22 and the negative 2 is going to come up to 20, and it's a 0. Once more, I will divide the second row on 1. So I will have the following shape, which is going to be a 0, then 1, 1, and 0. I will multiply negative 20 and add on the last row, it will disappear. Then I will multiply by negative 12 and add on the first row. Negative 12 plus negative 9, so it's going to come up to, I will multiply in positive 9. Positive 9 and the negative 9, the result is going to be 0. Positive 9 and negative 11, so it's going to come up to negative 2, and that's for the elements of the first row. Once more, I will go in order to get the span, the eigen of this eigenvector. So I would say this is eigenvector 2, first component, the second eigenvector, second component, the second eigenvector, third component. I'm going to try to expand. I will have the second eigenvector, first component, equal to 2, the second eigenvector, third component. For the second row, I will have second eigenvalue, second component, is equal to the negative of a second eigenvector, the third component. I can consider u2, 3 is equal to 1, and this how I can get the values, the eigenspan, the span of the eigenvectors. So I can say that u2 consists of u2 sub 1, u2 sub 2, and u2 sub 3. And then I will start making these substitution. Instead of u2 1, I will have 2 of u2 3. u2 2 will be negative u of 2 3, and that's u of 2 3. I will consider u2 3 to be equal to 1, so the results, it's going to come up to positive 2, negative 1, and the positive 1. That's for the second eigenvector. And the span of the second vector, exactly as I told you, it is with the span, which is going to come up to 2, negative 1, and positive 1. Exactly in a similar manner, I will go in order to evaluate the eigenvector relative to the eigenvalue, which is positive 3. So once more, if I want to do this, so it's going to be, just within a second. Yes, so I would go for the last step, having 4 minus 3, which is positive 1, 3 and the negative 7 and 0. For the second row, it's going to be 1. 2 minus 3 is going to be negative 1, positive 1 and 0. For the last row, it's going to be 2, 2. Then negative 3 minus 3 is going to be negative over 6 equal to 0. And same journey, I will use the first row in order to force the second and third to be zeros as the pivot of the first row. So simply it's going to be 1, 3, negative 7 over 0. Negative 1 plus 1 is going to be 0. Negative 3, negative 1 is going to be negative 4. This is going to be positive 7 plus 1, so it's going to come up to 8 and 0. In a similar manner, negative 2 plus 2 is going to be 0. Negative 6 plus 2, so it's going to come up to negative 4. Okay, so I've multiplied by negative 2, which is negative 6 plus 2. Negative 2 times negative 7 is going to be 14. 14 and negative 6, it will become 8 and 0. In a similar manner, I can eliminate the last row just by multiplying this and the adding. It will disappear. I will divide on negative 4, so it's going to be 0, 1. I believe negative 2 and 0. Then multiplying in 3 and the adding on the first row, so it's going to be 3. Negative 3. Negative 3 plus 3 is going to be 0. This is positive 6. Negative 7 is going to be negative 1 and 0 and 1. Now I can expand in order to get the eigenvector. The third one, which is U31, U32, U33. So it's going to be U3 sub 1 minus U33, U33 is equal to 1. Once more, this is the first component. This is 0, that's the third component, the third vector, third component. For the second row, it's going to come up to the third vector, second component, minus 2, the third vector, third component, equal to 0. From here, I can say that U31 is equal to U33, while U3 sub 2 is equal to U33. And I will use exactly the same procedure. For U3, I will have U3 first component, U3 second component, U3 third component. I will start to make the substitutions. So it's a U33, then 2U33, then U3 and 3, considering U33 by positive 1. So the span of U3 in this case, it's gonna be the vectors 1, 2, and 1. Now I can have the matrix B. Remark that the algebraic multiplicity is equal to the geometric multiplicity. The matrix B that I can use in order to make a diagonalization is here. The matrix B will be taking the first column at the vector, at the first vector, which is negative 1, 1, and 0. And taking the second column at the span of the second vector, eigenvector, which is going to be 2, negative 1, and positive 1. Then finally, I will have 1, 2, and 1. If I get the inverse of this matrix by anyhow, we already know how to get the inverses of this matrix, which is negative 1, 2, and 1, 1, negative 1, and 2, 0, double 1. Now I will find that the diagonal matrix, where its elements are the eigenvalues, which are 1, negative 1, and 3. Okay, this is 0, that's 0 and 0. This is also 0, and these are two zeros, is equal to P minus 1, simply, which is negative 1, 2, and 1, 1, negative 1, 2, 0, double 1, okay, negative, times the main matrix, which is 4, 3, and 7, 4, 3, and negative 7, times 1, 2, and 1, then finally 2, 2, and negative 3, times the matrix B, should be here, and this is how to diagonalize this problem. As you saw, we started by solving the equation. Sorry for the density problem, but we are solving a 3 by 3 system. We have a cubic equation, then we got the values of the lambdas, then we get the values of the eigenvectors. It has to be done this way in order to get the values as a vector. I will repeat the whole thing once more quickly, but by our slides, in order to get the values or to show you what we are going to do and the special cases related to this topic. We will have a couple of remarks that will make your life a lot easier in evaluating the values of the eigenvalues and the eigenvectors relative to these type of matrices. As I told you, this is really a very important topic, and we will see the problems down the road. So, first of all, that's after you solve your characteristic equation. You can analyze it. You will have lambdas equal to 1, lambdas equal to -2, lambdas equal to -3. So the main eigenvalues are 1, -1, and 3. Yes, Muhammad, you are right. I can, if I replaced the values -1, +1, and 3, or if I replaced 3, 1, and -1, the eigenvectors will be moved. So the columns will be moved. But the same result, I will have the same results. So they will move relative to each other. Okay, once more, the algebraic multiplicity of lambda is its multiplicity as a root of the characteristic equation. As you can see, there is none of them is repeated, so the algebraic multiplicity is just equal to 1. When lambda is equal to 1, I will take it and I will go for the system of equations, the homogeneous, and I can form quickly this equation. From it came 4 minus 1, 2 minus 1, -3 minus 1, it will give you this matrix. I will try to solve this matrix to reach a reduced echelon form. I ended up having this is U1 sub 1, U1 sub 2, U1 sub 3, or the vectors V1, V2, V3, whatever. I have the relation connecting them, and that's the span which is the first column. Similar manner, the geometric multiplicity is equal to 1, so the matrix is diagonizable if all of them this way. In a similar manner, I will go for when lambda is equal to +1 and do exactly the same steps for -1. Exactly, that's gonna be the matrix as we did. And also, after we solve, we will find the relation connecting the components. This is second eigenvector. The first component is equal to twice the third component. The second component is equal to the negative of the third component. I will be able to get the eigenspace, if you remark, 2, -1, and +1. Similar manner, I will go for the third value of a lambda and get the corresponding eigenspan, also eigenvector span, and we ended up as we are having here 1, 2, and 1, and also the geometric multiplicity is equal to the algebraic multiplicity, so it is diagonizable. Now we can get the B matrix, which could be formed from the eigenvectors. I will take the first vector, second, and third, concerning this is the first eigenvector.